Hey, I just wanted to talk to you a little bit about some issues to do with these, how to do the SPICE in problem 3 of homework 3. And so I just wanted to go over some of these things and a couple of issues that tend to come up. For one thing, make sure you go through and for each device put in the length and width, and notice that the default for that is in meters, so this is 1 micrometer. That's not going to matter for the level 1 model except for when you're doing capacitances, but that has to be put for each device, and the name of the device or the model in the device that you're looking at has to match the name of the model that, in my case, I just dropped it onto as a comment basically, or as a SPICE directive on the file there. Notice that the threshold voltage of p-channel devices is a negative number, so you might have to edit those. If you've done the problem, which I hope you have if you're watching this, you know that the nominal value of Vn that is approximately the required value to get all the transistors to be active is about 0.85. But one of the mistakes that people frequently make, and I'm trying to help you clear it up, is if you put that number in to a high gain amplifier, the probability is extremely high that the transistors will not all operate correctly because the gain from this input to this output node is so high that with this choice not done with extreme care, this voltage will either be too low or too high. And as in here, you can see that this voltage is too low because the voltage here is also too low. It's only at about 0.2 volts. That's lower than the VD SAT of M1, and similar, the output voltage is such that both M1 and M2 are in the triode region. So you can't just expect a very high gain circuit to bias itself automatically without knowing this number in more detail. So how can you figure that out? Well, if you've been around, you know that the answer is you need feedback. So I'm going to do two things, and I'm using the Mac version here. Let me put it over here. So one thing I want to do is just delete this connection temporarily, and then I have to make a connection, which is tedious. I'll just connect these two things. Now when I rerun this simulation, this thing is just floating. If I rerun the simulation, I've put markers on here, and lo and behold, this thing automatically goes to 0.84828, all those decimal places. This voltage is about what I designed it for. Notice that this voltage is about what we expected from the example. If I now say, okay, this was too high, I put 848 millivolts in here for this value. I just want you to see what will happen if we even do that. Now I've edited that value. I'm going to undo what I just did here a minute ago. So this is tedious again. I'm going to delete this. I'm going to put in a wire and reconnect this guy, and I can already tell you what's going to happen. This still is not going to work right. Watch what happens when I run this simulation. Again, we'll get rid of that. This voltage is at 2.66. This voltage is at 2.8. The VD SAT of M3 is not adequate. The lower transistors are in the right region, but the upper device is not really in the right region of operation. So what's the problem? This is not enough decimal places in this thing to even have this exact. So normally, if you do one of these simulations this way, and I actually did write down the exact right number of decimal places, 848,283, and I think that'll be enough to get us in the ballpark. All right, and now if I run this thing open loop with no feedback, again, I'll kill this. This voltage is at 0.854. Notice even now it's not exactly equal to what we expected, but it's close enough now that all the transistors are in the active region. If you now look at the SPICE error log file, which is not what I want to do, view SPICE error log, then you can see some of what's going on. The circuit has all the currents are at the desired value. That's easy. But getting the voltages is not guaranteed. Now, one thing you could do is look at all the VDSs and make sure that they're correct compared to the VD SATs. But when you're scanning these things real quick, a trick that I like to do is I looked at both of these and noticed that the GDS is much less than the GM for all of these transistors, and that's just a really quick way to scan for that. The ratio of those two things is our mu sub f, and it's in the ballpark of 100, just from the orders of magnitude of that. Then you could go through and get the voltage gain now by a number of things. If it's DC circuit like this, you could go through and edit out the comment to make this a .tf from this input to that output. Rerun the simulation. This is still a little kludgy in the SPICE version. If we add traces, it'll give us things like the transfer function, which is the gain, and it's inverting, and it's about 2500. I think I had calculated 2300, pretty close. And you can also, what was I going to do? Oh, I guess I got to run it again. I lost my thing here. The other thing I can do is plot the output resistance, which is one of the things we were asked for. So I have to add that as a trace. I think it's a little better implemented on the Windows version. And the output impedance is about 32 megohms, which I think is pretty close to what we thought. Okay, so those are some of the tricks. Now next time you should look, and I'll show you how to do the gain and the operating point all in one step, and you can find the loop gain. We did this last semester, and I'll reference you to a video where we talked about that, and we'll talk about it a little bit in class. Anyway, this is what I wanted to show you for right now. Okay, see you later.